All right, so that's the stuff that we will take a look at. So we're going to look at things from the fish's eye. And when I say fish, let's talk about sharks because it makes it more interesting. All right, so medium that the shark is in is going to be water, so it's got an index of refraction 1.33. So air is the second medium, so it's going to be 1. All right, let's figure out the critical angle first, and then we'll do a comparison. So the critical angle for water is going to be about 48, maybe let's make it 50 degrees. It's like 48.8 degrees that we're looking at. So it's 48, that's the critical angle. So if the angle of incidence is 40 degrees, so at 40 degrees, it's going to be refracted at 40 degrees. It's not going to be refracted. It's going to be reflected. So you end up getting an internal into water. It should say reflected into water. So you end up at 40 degrees, you end up getting an internal reflection. So which means that the fish, in this case, the shark, can see what's happening inside the water. At 48.8 degrees is the critical angle. So the shark can see what's on the water. And at 60 degrees, oh, I'm just messing things up. At 40 degrees, which is going to be smaller than 48, 49 degrees, obviously this is going to get refracted into air, not water. So they can see what's happening above the water line. At 48.8 degrees, it's going to be parallel to the boundary, so you can see what's on the water. At angles larger than the critical angle, it's going to get internally reflected, so they can also see what's in the water. So that they certainly have the upper hand. Shark certainly has the upper hand in general.
All right, now this experiment is going to start with 2 containers, and this first container I'm going to...
This is called refractive index matching.
Fill up with water. Most of the way up, there we go. That's about right. And the second container I'm going to use corn oil, about the same amount. Now that we have these containers ready to go, the next step is I'm going to add an empty test tube to each one. We'll put one in the water first, we can see it, and I'm going to fill it up with water. And there it goes. And we can still see it very plainly. Now let's try one in the oil. Get one here. There it is. Put it in the oil. We can see that very plainly, but let's fill it up. And the test tube seems to disappear. Now let's see that again. Here we are in the water. Fill it up. There it is, plain as day. We can see it very easily. Let's try the oil again. While it's empty, we can see it very plainly. But once that fills up with oil, it seems to disappear.
All right, so the question is why? The reason why this happens is because this glass is the same index of refraction as this fluid does.
Now the answer is it has the same index of refraction.
So, which means that the light
as the oil does.
Goes right through.
And that means they both bend light the same way at the same angle.
Which means that the light goes straight through.
So that's what's making it hard to see the test tube inside the oil. Now that you understand this concept, we're going to take this broken.
And this was the little magical observation that we started the lecture with. All right, so if you put these on the inside, obviously you're not going to be able to see it. And if you have a whole tube next to it, it looks like this got replaced with the whole unbroken tube.
Test tube and make the oil appear to make it. All right, now this experiment.
There's a second version of the same experiment. So what do we have here? We got glass. And then you place that material, which is very much denser, heavier, or whatever. And naturally, it's going to keep going down while pushing the glass in the upward direction. Notice that it's slowly moving. And then if you put some kind of fluid in it, which matches the index of refraction of the material on the inside, the light no longer bends. It's just simply going to go through the material. So the material itself is going to become invisible to us. There you go. So this is called index of refraction matching. Different version of the same experiment. Break the glass. He says corn oil, corn syrup. I don't know what that is, but it certainly has the index of refraction of glass. But as a result, the light is going to go right through. Fake diamond versus the real one. Fake diamond has the index of refraction, which is identical to corn syrup. That's what I'm going to say. It could be corn oil. All right, so if you have fake diamond, place it into corn syrup or corn oil. It's going to completely vanish. Mirages. What caused that to happen? All right, so the cooler air mass, the hot air, I noticed that it's definitely going to change the density of air, and how fast the light travels is sensitive to the density of air. And the brain has a tendency to see things in a straight line, obviously. All right, so density of air is going to change the speed of light. As a result, you end up getting these aberrations from a straight line. And then in turn is going to cause mirage, which means that your mind is going to make up. Your mind likes to see things in a straight line, so it's going to make up some kind of reality.
Other miracle stories may also have scientific explanations. When Jesus walked on water over the Sea of Galilee, his disciples took it as proof of Jesus' divinity.
Oh yes, the walking on water. Well, that's of course an excellent example of the inferior mirage, where one sees a hot surface that apparently reflects the sky beyond it, and you interpret this reflection of the sky as a pool of water.
Inferior mirages are low-level atmospheric phenomena that can happen over water or land. When the air just above the surface is hotter than the air a few meters higher up, the conditions are right for this confounding optical illusion. Light rays passing through the atmosphere bend with the variations of temperature, and wavering double images appear near the surface.
Everything that you see in a mirage is a distorted image of something that's really out there, caused by the fact that light rays are not taking straight line paths through the atmosphere.
The human mind may interpret these images as reflections in water, yet the pavement in the sea is actually bone dry. A superior mirage causes things to appear higher than they actually are. These ice walls, known to sailors as the Fata Morgana, are actually a reflection of the surface ice. They don't really exist.
Dispersion is the breaking the light into its color components. You got the white light going through a prism. It's going to break down into its color components. Red is going to be on top. The violet is going to be at the bottom. The reason why this happens is obviously red must be traveling faster than violet because it's bending less. So the question is, why is it that red travels faster than violet?
Refraction occurs when light enters a medium, such as glass, and bends. To make use of this phenomenon, makers of glasses, microscopes, and telescopes can grind curved lenses that focus light to a point. But before that, it's possible to see refraction in its natural state. And here's a clear-cut example. A glass prism not only bends or refracts a beam of light, it also reveals that plain white light is composed of all colors of the rainbow. This process is called dispersion.
So the question is what causes it? So you have the incident light going through the prism. It's going to break down into its color components. Red is bending less than violet, which means that the red is moving faster through the material than violet. Red also has a larger wavelength than the violet. So what gives if that's the case? All right, so what gives if that's the case is different wavelengths are experiencing different indices of refraction. So translated to English, what that means is different wavelengths are traveling at different speeds. The larger wavelengths are traveling faster. Their indices of refraction is smaller. All right, so the question is, why is it that the larger wavelengths travel faster? Explanation is straightforward. We'll get that out of the math. So we're dealing with dispersion. So which is the separation of light into its color components through a prism in this case. And we can express the wave speed as a combination of its wavelength and frequency. And we know that the wavelength is sensitive to the index of refraction. So the larger the index of refraction is, the smaller the wavelength is going to become. So which means that for a given frequency, the larger wavelengths will travel faster through the material. So for a given frequency, the larger wavelengths will travel faster through the material. So the red has a larger wavelength, therefore, red is actually going to travel faster through the material than violet will. All right, so it's going to travel through the material faster than violet. Okay, let's get back to. All right, so they will travel faster through the material. I think I missed something. Okay, so let's go back. All right, so red is going to travel faster. So the index of refraction influences the wavelength. Smaller the index of refraction is, the larger the wavelength is. That's a mathematical way of looking at it, which I don't really appreciate because it's kind of misleading. The reality of it is the larger wavelengths are traveling faster through the material, therefore they will have a smaller index of refraction. So yeah, I'm just trying to correct that statement. I'm saying the larger the wavelength is, the smaller the index of refraction is going to be. So translated to English, what that means is the larger wavelengths will travel through the material faster. So that becomes our conclusion. So the larger wavelengths will travel through the material faster, therefore they will have smaller indices of refraction. All right, and that's what it means. Smaller index of refraction, and translated to English means they are moving faster. And that's the main cause of dispersion. That is the main cause of dispersion. rainbow is an interesting phenomenon because at the top you will see red, at the bottom you will see violet in reality. So what's causing the separation in essence? All right, what's responsible for the rainbow is these water droplets up in the air. So you got the sunlight coming from the sun, entering into your density medium, so there's going to be a refraction. And the sunlight is going to break down into its color components. Because of refraction, you end up getting dispersion. And because they will hit the boundary in an angle larger than the critical angle, whatever that critical angle is, when the light hits a boundary larger than the critical angle, it's going to get internally reflected. And then it gets reflected out again. All right, so it happens just like that. So there's going to be a color separation of light, dispersion. So you got the refraction, internal reflection, refraction again. And now the red is going to be at the bottom, the violet is going to be on top, in essence, after the dispersion takes place. Now you have to look at it from the perspective of the person who's looking at these water droplets. All right, so you got a water droplet on top, so the light gets refracted, reflected, and refracted again. So the red is going to come from this way. From the water droplets down below, I this time is going to be able to intercept the violet. All right, so notice that the violet is going to be at the bottom as a result. The red is going to be on top. All right, so this is the way this human eye makes up its reality, in essence. And as a result, when you're looking at the rainbow, the red is going to appear on top, the violet is going to appear at the bottom. And this is caused by the dispersion. Refraction, internal reflection, and then refraction again. And within the material itself, the light just breaking into its color components, which is the dispersion phenomenon.
One of the most celebrated atmospheric optical effects is the rainbow. When sunlight meets almost perfectly round raindrops in the atmosphere, the light is refracted or bent as it comes out. As light of different wavelengths is bent to slightly differing degrees, the color spectrum is liberated, becoming a brilliant multi-hued arc. But why is the rainbow visible only when our back is to the sun? It has to do with our position between the sun and the raindrops in the sky.
Now, there's a point in space which is exactly opposite the sun. It would be marked by the shadow of your head on the ground. I'll call that the anti-solar point. The rainbow lies on a circle which is centered on the anti-solar point. And so you see that portion of the rainbow circle which is above the horizon.
Unrestricted by the horizon, a dramatically different rainbow can be seen.
For instance, if you were in an airplane looking at the sun shining on a rain sheet, in principle you could see the whole circle. Now, that's a kind of a rare thing. You have to be sitting in the pilot's seat, not in the passenger seat, to be able to see that wide angle. But in theory, the rainbow can be a complete circle.
Astronomer Andrew Young of San Diego State University says that rainbows are a totally personal experience.
No two people ever see the same rainbow because one person standing here sees the raindrops that are over here, and the other person standing here sees the raindrops that are over here, and all these raindrops are illuminated by the same sun, but there's this fixed angular deviation of the sunlight, so each person sees a different set of raindrops illuminated by the sun.
Why is the sky blue? Given the fact that the light from the sun is actually white, if you're looking at it without the distortions of the atmosphere directly, because the light, sun is the source of light. If you combine all the colors into one single color, you end up getting white. The reason why we end up getting blue sky is because of the simple reason that the yellow light gets subtracted from the color spectrum as it's going through the atmosphere, because the blue light gets scattered. It gets scattered away by the molecules making up the atmosphere more than any other color. All right, so this is known as diffraction, something that we will discuss later. In modern physics, this is also known as scattering. Diffraction phenomena is going to be related to the wavelength and its relationship to the sizes of the openings or the obstacles that we're looking at. So diffraction is how much the light wave is going to deviate from a straight path. As the size of the wavelength is actually significantly smaller than the size of the opening, notice that there's not much of a deviation that takes place, so it's going to keep on moving in a straight line. But when you actually make the size of the opening on the obstacle the size of the wavelength, immediately you're going to start to get these deviations from a straight line. So this is known as, you can call it scattering, obviously, or it's called diffraction. So if the wavelength is significantly larger than the size of the opening, or whatever, and once again, you end up getting more of a diffraction out of that.